Sounds good. You're good to go.
Okay, so welcome to part two of my presentation on basically going through two papers that use graph partitioning methods to enhance greedy packing. Um, Last week I went through this paper, Improving Timing-Driven FPGA Packing with Physical Information, and what they did was they used a graph partitioning tool called hMetis to basically do a rough global placement of everything. And then they used this global placement to guide the packing. This week, I'm going to talk about this other paper, how preserving circuit design hierarchy during FPGA packing leads to better performance. They also do the same thing in some sense of the word, in that they use graph partitioning. Uh, the way they use it to guide packing is very harsh, I guess. So if things are in the same partition, they can be packed together. If not, they're not packed together at all. So to basically get to it, the algorithm they made is called multipart. The main idea is that they do this partitioning and then they pack each of the partitions independently and in parallel. So unlike the previous algorithm called DPAC and HDPAC, this is in the heterogeneous FPGA era. And so it adds some complexity. You need to account for that and when you're partitioning. So for example, partitioning memory is dangerous. And here you can see in this figure, they basically do a recursive bipartitioning again. They partition things in two. They have this hard block swap stage that I'll talk about later. And then they partition the resulting partitions in two until they get to some partition size that they deem a limit. And then they just call AA pack to pack that.
A quick question, Amir. I don't know if you're going to cover this in a future slide, but partitioning memories is dangerous. What does that mean?
Um, Essentially, if you uh, so for example, you have 9 memory slices. I guess this is something that I'll talk about more in the future slides. But for example, if you have 2 memory slices that could have been in the same memory block together, but then you put them in separate partitions, now they will use 2 memory blocks instead of just one. So that's just an example.
I see. Thank you.
So hierarchical circuit by partitioning, you partition the circuit into two parts. And the goal is to minimize the number of cut edges. And then you have an unbalance factor. And the unbalance factor is basically, so when I have two partitions, how bigger than the other one can be. So do I want my two partitions to be exactly the same size, or do I have some threshold of maybe like 10%, uh, uh, one can be 10% bigger than the other. So that's something um, they do a sweep to find out like what's the best number for the ambulance factor in this flow. And then you recursively do it again for the resulting parts. And the goal is to split the circuit into weakly interconnected subcircuits. So for example, in this figure, we have these three subcircuits. They do have connections together, but like if you take the top left partition or cluster here, they're very strongly connected to each other. They have one connection, like two connections to the outside, but they're weakly connected in a sense and not as strongly connected. And the goal with this bipartitioning is to get these weakly interconnected subcircuits. And then finally, you just pack the subcircuits independently. So you have some problems, and they identified some problems with this naive approach. You have a problem of resource quantization, and that the resource in the FPGA architecture cannot be shared between the subcircuits because they are all packed independently. What that means is you cannot pack, so for example, you have a CLB that can have like 4 primitives together. And these 4 primitives can only be from one of the subcircuits. So different subcircuits cannot share a CLB, essentially. And this means that the total number of CLBs used in your design will go higher. Difficult selection of RAM types. So all subcircuits are packed concurrently. No information is available on the FPGA resources used by other subcircuits. This leads to a problem for RAM primitives because they can be packed into multiple RAM blocks. The specific example is that they give is for the Titan architecture, where you have the 9 kilobyte RAM and the 144 kilobyte RAM. So what they do is they essentially just call VPR, call 10 VPR processes, like they just run 10 VPR processes for each 10 of their subcircuits. And so each VPR instance thinks that, okay, I have 100 M9Ks, and and I can only use like 10 of them. Or let's say this device has 100 M9Ks and I can only use 15 of them with the subcircuit I have. So everything gets assigned to the M9Ks. But then you add all these 10 VPR instances together and then you run out of M9Ks. So that's something they need to take care of. And the runtime overhead. So because they run 10 instances of VPR, for example, uh, just running VPR 10 times incurs some overhead. You need to generate and like all these data structures. I don't think they mean the R graph specifically, but all the other data structures.
The other graph wouldn't be built until they stop after packing.
Yeah.
So it's interesting, these process level parallels, they actually invoke multiple VPRs.
They invoke multiple VPR. Yeah. So yeah, there's some runtime overhead they have to incur for like calling 10 VPR instances. All these data structures need to be generated like 10 times. And then you have the problem of you lack correct timing analysis. So for example, these cut edges don't exist in the netlist that they give to each instance. So for example, if you have a critical path here that was cut, then the VPR instances don't really think of it as a critical path anymore because it's a pretty short path now because like we cut some of the path.
Wait, that's so interesting. So they're invoking VPR as like an external tool, and then they are basically feeding it a fake netlist for each subcircuit to get a packing.
Yes.
And there is a way you could put delays on those edges by basically adding like constraints to an SDC file. Do they talk about
That's
that?
what they do.
Oh, that is what they do. Okay, perfect.
Cool. Well, so for the research quantization problems, they essentially they don't really say like the exact wording is that we adopted the pre-pracker from VPR. So, but I'm not entirely sure. Do they just call VPR once and use the pre-packing info, or do they like made their own pre-packer logic or whatever? But they do essentially the pre-packing stage, and they group atoms into molecules, and they only partition molecules and not atoms. So this kind of helps with the resource problem. For memory packing, so this is one part of the memory issue in which like each VPR instance think it has enough M9Ks, so it uses all the M9Ks, but in aggregate, you don't have enough M9Ks. They assign a memory block to each memory molecule before partitioning. So if a memory slice fits in an M9K, you assign it to an M9K and M144K otherwise. And if you don't have enough M9Ks in a device to accommodate the circuits, you change some of the slices to a M144K until the problem is solved. For mitigating the VPR overhead, they removed unused blocks and modes from the device's specifications. So if you have some unused mode in your circuit, they just don't generate it. Not entirely sure how they do it, but that's what they say they do. Um, And yeah, I already explained it, but in the paper they say you run an AAPAC thread. What this means is that they run VPR with dash dash pack. Parallelization is just running multiple processes of VPR. So, for memories, we have another problem, and not just memories, for just hard blocks like memories, DSPs, and all that. There is another problem. So, for an example, if you have M memory slices with the same address and control, and you partition these into M different subcircuits, then you use M memory blocks instead of just one. So, this is, I guess, they mostly focus on a Titan architecture. And in that architecture, all memory slices that share the same address and control signals, they can be packed together into the same RAM block as long as the depth of the block is large enough.
It's pretty true.
Yeah.
Kind of most or all FPGA block memories
Yeah.
too. I guess the key constraint.
And a DSP block is able to implement two DSP molecules. This is something that they say, I'm not entirely sure which architecture they mean, but
It's probably discussed before,
yeah.
actually, that comes with Titan. That's the way, not always too, let me think about that. It actually depends on the mode. So that architecture should be like, I think about Stratus for again. But I believe it can do 4 9x9s, 2 18x18s, 1 36x36. So actually, the number of things you put in depends on what you're trying to stick in there. And then the way Quartus represents this is with a map mult primitive, which is the multiplier, and then a mac out that represents everything else that you do an accumulator after. So those get tied together. And if you're doing something like a 36x36 one, you'll get, okay, now let's say you're adding together 4 9x9 multipliers. You get 4 mac mults and then 1 mac out, adding them all together. So you wind up with two kinds of primitives going in, some of which have to be chained together if there's some complicated things. So I'm not sure why they say it's like there's two types of molecules, or two types of primitives go there. They're not always gonna be two things there won't always be two molecules. Sometimes it'll be a different number.
Okay. So the way they fix this is after each partitioning step, they swap the memory and DSP parameters around different partitions to keep the total number of blocks constant. So for example, we have 8 memory slices in this figure. They share address and control, and for example, let's say each memory block can like pack 3 memory slices. So here we don't do anything, we just cut. So at the very start, we had 1, 2, 3, 4, 5, 6, 7, 8 memory slices. And then, so dividing that by 3, we realized that we need 3 memory blocks to pack this, for this many memory slices. After we partition, we get these subcircuits. So this subcircuit needs 2 memory slices. This one needs 1, this one needs 1, and this one also needs 1. And in total, we need 5 memory slices instead of 3. So we have an explosion of RAM here. What they do is after each stage of partitioning, so for example, in here in the left side of this B, so you have 5 slices. So this means that we need 2 here at least. If we move the one of the so okay, let's I guess I went from the wrong way here. So we got to this mid-level stage and everything was fine. The total number of memory blocks was good, nothing went wrong here. But in the next step, when we want to cut here, now we have one subcircuit with just one memory slice, another with 4 memory slices. In total, that means 3. But before we did the cut, we could do it in 2. So we had an increase in the number of RAM blocks needed here. This they use this increase to say that, hey, we need to move things around to fix this. And if we move one memory slice from this lower cut line to the other side of the cut line, that gets fixed. So here, this subcircuit has 3 memory slices, 1 memory block. That's great. This one has 2, 1 memory block. Again, that's great. And if we move just this one memory slice to the other partition, then this has 0 and this has 3. So in total, we have 3 memory slices, same as if we haven't partitioned it at all. So that's how they fix the explosion in the number of memories. And then timing-driven multipart, not a lot of details on how exactly they did the timing analysis, but they add criticality information to avoid cutting critical edges during partitioning. And they do that by adding timing edges. So they add extra edges with like the weights they set using the criticality of the path. They just add new edges to the net list and use that to avoid cutting the critical edges. And they also use STC constraints to do exactly what Alex said, to basically tell VPR that, hey, I know you don't have information here, but this is critical, trust me. And they get 3% better CPD doing that versus not doing that.
Do they use like set input delay and set output delay? Is there SDC commands or not?
I don't think they really said
They
exactly
don't
what
say
they do.
exactly what they do?
Yeah.
Okay.
The code is open source. It's actually like Java based, so they like call VPR in this Java code base. That's how I found out they actually just call VPR and not like running threads. But I haven't
If
really
you
looked
did
into
one
that.
timing analysis of the whole graph, you could get basically what's the arrival time at every node that you're cutting when it's going in, and you can mark that as your set input delay, and you get the downstream time, like kind of the required time. So the required time? It's almost whatever delay is coming after your output, you mark that as a set output delay, and you're essentially modeling what's happening in the rest of the netlist now. So by putting delays on your inputs and outputs. You don't update with anything that happens to the rest of the netlist, but if you just did one timing analysis and said, find the longest path to every single input cut and mark that with like a set input delay, it is accurate if none of those outside delays change.
Yeah, the one question I have on that is, what if I cut something that has like a setup constraint or hold constraint? I assume I don't even know if that's possible. So I'm trying to like think it through. Obviously, they're not going to cut a clock signal, but like for example, let's say I had a reset signal that goes from logic into a reset signal, and that reset is asynchronous. Would that have like setup and hold implications, and do they handle that?
I doubt they handle that, but I also don't think it's a big deal because they're so early in the flow that anything you don't understand, you probably don't know what to do with anyway.
Yeah,
And you kind of go, who knows what to do with that, so we'll just ignore it and let the downstream parts handle it.
makes
Uh,
sense.
That's basically the correct thing I think to do for clocks. And asynchronous reset is a little, it's kind of, well, this asynchronous reset, it just behaves like a regular signal. It's
Mm,
asynchronous, different analysis, but I guess you just rely on the timing analysis tool to do the right thing.
right. Hmm.
Okay, and
I mean, I guess they will lose some information in terms of like, if they pass a lot of stuff, which they're probably not doing. If you had lots of overlapping clocks and so on, then you have to pass more information to reconstruct that on the other circuit. But it's also relatively rare to have lots of overlapping clocks, like clocks whose timing paths overlap. Like usually your timing paths are within a clock domain with a few in between. I don't know if that made any sense to anyone or not, but I'll stop talking about that if it's not making sense to you.
I was a bit confused, but
Okay, don't
I
worry.
think yeah. Okay, thanks Juan for the explanations. So getting to the results. First, they explore like what exactly would be the best unbalance factor and like how much should we partition things. So for unbalance factor, they realize that the more freedom they give to the partitioner, the better quality they get. But there's also like it should be balanced by the runtime also, because if you have one really massive partition and then you have another partition with like two molecules inside, it's you don't get any runtime games on that, so it's almost like if you didn't partition at all. They realized that they say that 25% was a good number and they stick to that. And partition depth is so they have this n max factor is which basically says that whenever a partition has less than this number of molecules, stop partitioning it. So they stop at, for example, each partition size is at most 30,000. You get this result. Each partition size is 2,500. You get these results. So they realize that there's also a runtime thingy here going on. Um, so the partitioning takes longer when you partition more things, obviously, but it's the number isn't very high, so it doesn't get twice as bad. And the packer becomes faster because it needs to partition less things together, and also because they're running it in parallel. So I think that's what's happening. Wait, no, this is actually like one partitioning instance, I believe. So QR wise, you see an improvement in both wire length and CPD. They found out that 2,500 is a good middle ground here to just stop at because you lose a lot of density here as you go to like 725 number of subcircuits, 725 partitions. You lose like 6% of the density. So they said that 2,500 good enough. We're just going to use that. They get like 32% better wire length and 10% better CPD. So here are the results. Parallelized, they use 10 cores and the same number of partitions as before. The unbalance factor and the number of partitions is as explained before. So they get around 10x speed up. Routing is much better, so they avoid, I guess, a lot of congestion problems here. And wire length is also like very much improved. So 10% improved in CPD, 32% in wire length, 10x speed up in pack, 40% of speed up in route, and 7% of speed up in placement time, um, which is great.
Quick question, Amir. What is baseline?
So the baseline here, exactly. So baseline here is VTR7. And essentially, if you read the VTR8 paper, you get almost exactly the same numbers, like between VTR7 and 8. So basically, like
What about the packing runtime? Basically,
not the backing runtime, no, the quality wise, I mean, yeah. So this is based on VTR7, which did not have the best quality, I guess, and the packer was also
Packer was
very too aggressive. Yes,
Yeah,
it was
don't
incredibly
believe that.
dense.
The two the packer in place was a big thing, the packer was too aggressive, so dialing that back on unrelated logic made a big difference.
Yeah. So essentially, like the results for the previous paper, I guess, a lot of the quality benefits here could be attributed to the fact that they made the packer less aggressive and less dense. And so I did basically the same thing. I didn't use hMetis and like I didn't use recursive bipartitioning. I used the graph partitioning to do a minimum cut and like I told it to, hey, give me 16 partitions. And so I didn't do two partitions like 4 times. And I did not get the same results. Like I could not recreate these results. And I feel like that's because like my baseline is like VTR9 and theirs was VTR7. So any questions?
So early on, you talked about the RAMs. So you talked about two things in the RAMs. One was the hard block. Think of what you bloat as you're partitioning with the hard blocks. The other one was you also, they pre-decided what kind of RAM you target.
Yeah.
And so they do that, I guess, with just like a bit counting kind of routine. They say like how do they do that? Do they run like their own little pack or an AA pack? What do they do?
They say if a RAM slice fits in the M9K, we put it in there first.
So maybe they just do that with just count the bits basically.
That's probably, yeah.
Okay.
If it fits, they assign it to a 9 kilobyte kilobit RAM, and if not, then
Okay, so they do sort of a balancing up front.
Yeah.
Because once they run out of those, then they do 144K, and then they basically mark that somewhere, the APAC has to respect that later. So
Yeah, maybe even like they well,
I'm
yeah,
guessing that's what they
probably,
do,
yeah.
but they do it with some quick, this looks compatible, let's reassign it. It's not a bad idea, like something that's weak about APAC with multiple RAM types is it just kind of greedily packs them until it runs out of one, and then it goes like a smart this open to something else. And that's not that smart. I'm not sure even if how we order, like to order what you're packing, and you have these heuristics of what do you pick as the thing you're gonna stick it in. But it's a bit chaotic, like, I don't know if we could wind up putting like relatively large RAM slices in relatively small RAMs and vice versa. And then once we run out of one kind, we'll basically stop using it, so we'll adapt that way, but we didn't sort of forecast what was coming.
Hmm.
Like this maybe not be very smart of, this is a pretty big RAM and I stuck it in a pretty small RAM block. It will fit, but it takes the whole thing. And instead I could have, there's a whole bunch of RAM slices just like this one. I can put the whole thing in a big physical RAM, right? And APAC doesn't understand that. So anyway, they're not quite doing that either. They have also a simple heuristic, but the balancing is smart, and the partitioner could make this worse.
Yeah.
Yeah, I also had a comment on this. So when I was doing my own experiments, I found a very similar result to what they're doing. If you start to partition RAMs too early, even before packing, without knowing, like, they share these signals, they share these clocks and so on, you end up exploding the number of RAMs. I was finding like it more than doubled for a lot of my test circuits that I was doing. So I agree with Vaughn actually a lot on this because if we could just predict beforehand, I believe how the Packer does this right this second is that it will take a seed RAM slice, it will go through each mode one by one in order of the XML file, try to pack it in the first mode, doesn't work, try to pack it in the second mode, doesn't work, and so on or the logical block type. So it will do the M9K, then the M144K, and so on. And if that's how it decides which ones to do, and then any other molecules it wants to bring in, it then tries to put it into that logical block type that it chose at the beginning. And so, yeah, that could explode your memory if you, as Vaughn said, if you try to do, if the order changes, which explains why the seed selection was causing problems for me. And then also if you don't allow things to come together. So yeah, that makes a lot of sense.
Also, what you said, like it's just going through one mode after the other in order. So that means how you wrote the modes, like you should write like the shallowest mode first.
Right.
You actually would just go in and say, hey, I've got lots of address bits. I love this. We get one RAM slice in, but that's somebody else's problem. Um, so that's also dangerous. It's kind of like it's okay if you write it one way, but not okay if you write the architecture file reversed.
Right. I think this reveals the packing issues they were running into reveals that we RAM packing in VTR like the AA pack still has these problems. So it would be interesting to look into how packing can be improved for these more complicated blocks with these very special constraints.
Yeah, I agree.
Hmm.
We should find a victim to take this on.
It has the opportunity for a lot of improvements because, yeah, I mean, just counting the bits is probably a good idea.
Yeah, no, we should do a better job on this. So somebody gets excited about doing it, we should just do it. So
Mm.
there
I
we
think
go.
the solution we're going with right now is so far is okay.
Sorry, Alex. What did you say? I didn't quite hear you.
Oh, sorry. I said I think the solution we have right now should be fine. And because right now the packing is doing a good job with how it chooses RAMs, it seems like whoever made the seed selection logic and wrote the XML files have chosen it in a way that creates okay RAMs. But I agree with Vaughn. Stability is important.
This is like, I just read this paper to get ready for this too, actually. It seems like quite a nice paper. Like,
It is pretty well written, yes.
yeah, I think it's got a bunch of interesting things in it. I'd say what they're doing to avoid exploding the hard blocks is quite clever.
Yeah,
Whereas they're
the
partitioning, they're kind
well
of doing
played.
a look ahead of should I rebalance this to avoid like stranding things later on. So yeah, it's neat.
Yes. They also had very pretty figures.
Was that first figure like that you had from their paper or did you?
I
draw
think
it?
every figure I had was from their paper. Like this is theirs, and this is theirs. This is also theirs.
It's a nice
Yeah,
figure. I
it's
like that
pretty
figure.
good.
It's great.
Yeah.
So,
Yeah, it basically shows the entire algorithm in one figure, and it's very neat.
yeah, it's nice.
Yeah. Oh, and Vaughn, I did want to confirm something. You were talking about how the Stratix 4 architecture capture models DSPs, so like two DSPs per. Looking at the architecture, the DSP logical block has two half DSPs, and I think that's what they're referring to. But within a half DSP, you can have four MAC multipliers, and that I think is controlled by synthesis.
Okay. I mean, that's like saying somebody's trying to work and have updated multipliers.
Yeah,
Divided into two groups of four, basically.
yeah, that's what I think is going on as well.
Yeah, that makes sense. Okay, I guess that'll be it for today. That was a shorter group meeting, reading group, but yeah.
Cool.
Gotcha. Thank you so much, Amir.